Hello, this is an attempt to derive the kinetic energy equation often quoted in physics books. Kinetic energy is equal to a half mv squared, so the kinetic energy of a particle is equal to its mass times its velocity squared. So velocity is just like its speed in a given direction. So I'm going to prove this using nothing else apart from Newton's second law and a bit of calculus. So we know that Newton's second law is F equals ma. So the force on a body or particle is equal to its mass times by its acceleration, so that's its change in velocity over a given time. We also know that the energy of a body is equal to its the force on it multiplied by its displacement. So we can times both sides by s, so we can get force times s is equal to ma times s. So that's just using Newton's second law. It actually turns out that saying that the kinetic energy is equal to the force times displacement is an oversimplification if the force is not constant. If the force is variable, we can't assume that the total energy is going to be equal to the average force multiplied by its displacement, because the force varies so much that we can't say that the average force is going to be the same as all the individual forces times by all the individual displacements over the displacement is going to be the same. So what we actually have is an area under this force displacement graph as being the energy. If you take a very small section of the graph, when the force we can say is constant over a very small amount of time, and then the energy is equal to force times displacement equation still holds, because over that very small amount of displacement the force is still constant because it's a very small amount of displacement. So the energy is going to be equal to the force times that small displacement. So obviously you can see that over a varied force, then the energy is going to be equal to the total area under the graph, which is kind of like summing little sections of the graph where we can assume the force to be constant. I've actually put an equation down to try and understand this more. What we've got is the energy is equal to the sum of all the forces times by the little changes in their displacement. I mean, what we can say is delta s is very small, so the value of delta s is going to be a constant, very small value, and the force, like on the graph that I showed you previously, is going to be the force of that particular displacement. So if we multiply the force by the change in the displacement, which is very small, we've got the energy at that point, and this is from E equals F times S. And the summation starts at S equals 0, which is a displacement of 0, and ends at S equals m, which is a particular value of displacement. So that's why the equation E equals Fs holds over some variable force. So we use the summation. Of course, if we've got a change in S, which is delta S, we can transform this equation into an integral. So we can say that the energy is actually equal to the integral of force with respect to displacement, and that's over these two particular values from 0 to n. I mean, this is an indefinite integral, so what we're saying is we're taking the area of that graph I showed you from n, which is a particular value of displacement, to 0, which is before the particle started to move. Okay. So having ascertained that we've got the energy is equal to the force with respect to displacement, we can substitute F for ma. So these two integrals are going to be the same, and that's simply using Newton's second law, which I've already showed you. But you'll notice that the integral on the right is not presently solvable. We know what the integral on the left is because that's just equal to energy, but we don't know what the integral on the right is because we've got a respect to displacement and we've got an acceleration, so that integral is not solvable. So we're going to have to use Newton's second law again to try and put that integral into a nicer form. So F equals ma. We can say that A is the derivative of velocity with respect to time, because acceleration is a change in velocity over time. I mean, we know that if you're accelerating, your speed or velocity is going to be changing. Okay, so that's how that simply works. Of course, we can use the chain rule to change dv dt, which is our velocity with respect to time. to dv ds multiplied by ds dt. You'll notice the ds's cancel out. So that's just using the chain rule. Okay, so if we put this back into our integral, we're going to say that the integral of ma with respect to ds is equal to the integral of m dv ds times ds dt with respect to s. Now the next bit is we can say that we have on the right hand side we've got the differential ds over dt, which is the derivative of displacement with respect to time. So the change in distance, the change in displacement over time, and we know that that's equal to velocity, because if your displacement is changing, then you've got a speed or a constant speed. So we know that speed equals distance over time. So we know that a change in displacement over time is going to be equal to velocity. So all I've done below is simply substituted ds over dt with v. So we've got now the integral of ma with respect to ds is equal to the integral of mv dv ds with respect to s, and you'll notice that the two ds's cancel out. So now we have a much nicer integral. We've got the integral of ma ds is equal to the integral of mv dv, which, as we've ascertained at the start, is still equal to the integral of f ds, which is equal to energy. So now we can solve the integral mv dv, and you'll notice that the integral of v, because m is just a constant, because it's just mass, you notice that the integral of v is a half mv squared. So the integral of ma with respect to s is equal to the integral of f ds, which is equal to a half mv squared. So we can say that the energy, or the integral of s ds, is equal to half mv squared, which is kinetic energy, because the only variable involved in the equation is the velocity. So that's a particular equation for energy in terms of its velocity, kinetic energy. I hope this has been interesting. If anyone can see any mistakes that I made on this, then please tell me, because I don't want to be talking rubbish on the internet or whatever. So hope that's been reasonably interesting. Thanks.